So here we are at it again. Last time I left it at me trying to understand where things are being learned at all. I'm like I'm completely lost in terms of how is that then going to be structured from a code perspective. I thought these, so I thought it could be the way that some of the value tensors in the attention weight. So I thought, analyze attention scores. So we have the attention scores, but then I thought this output was supposed to be the output. Compute the weighted sum of the values, or the values tensors, or the value tensors, using the attention weights. These are the value tensors. As in like QKV, the V, right? But then the output, attention weights and output. So I have the attention weights, and I'm currently not doing anything with the output, right? So this is the call here, multi-head tension, the call, and I'm not doing anything with the output, just the shape. And what was the shape of the output? Applied weights, 4, 15, 10. So it's essentially the same like these one, 4, then 15, and then the 10 dimensions of each. No, 15 is, sorry, 15 is the max length, yeah. And 10 is the D model. Exactly. But this is what is in theory supposed to give me. That's like, you can't imagine the gap that I have in my head right now. So like I feel totally lost. So this is essentially gonna, I have the attention weights, but how is that calculating the, how is that making a prediction, right? It needs to, so how do I go from attention weights to prediction, right? So so in the multi-head attention layer of the transformers architecture, hopefully the sound of the laptop is not just too loud. Sorry guys, because I'm not having the best setup as I'm not really at home. In the multi-head attention layer of the transformers architecture, how do we go from having the attention weights to making a prediction of the next word? You know what I mean? This is maybe the best way to actually, the multi-head attention layer of the architecture, after computing the attention weights, are used to produce a weighted sum of the values for each query. So these are the values. This is a weighted sum. Okay, a weighted sum of the values. But then the values are what? Because so far the values have just been a projection of the input as well, which is what I don't understand. For each query, the attention output is then concatenated across all attention heads and passed through a dense layer to produce a final prediction. In our implementation, the attention output is obtained on line 96. Kind of, sort of, okay. Which is then reshaped line 98. We're ready for multiplication with the following dense layer, which outputs a vector of the dimension of. You see, that's the problem. I've got something wrong here. So to be ready for multiplication with the following dense layer, which outputs a vector of the dimension of the output vocabulary. Do these things need to have like an actual vocabulary? That's a good question. Actually, I didn't think about these. Do these things need to have like an actual vocabulary? So currently, okay, so because currently what I have is so what is V used for in here? It's used for nothing. It's used like here at the end, chat. So what should I use as Q and V values? I assumed, or in the implementation, I start off by assigning the same input tensor to all of these. But should V be some sort of vocabulary? That's what I'm. So in multi-head attention, QK and V are the query key and value tensors respectively. In our current condition, we use the same tensor access input for all of them. I'm building a language model with transformers architecture. The Q and K values are usually tokens from the input language. What? Oh. When building a language model using transformers architecture, the Q and K values are usually tokens from the input language, and the V values are the corresponding embeddings which represent the meaning or context of each token. Therefore, the V tensor is typically derived from an embedding layer that maps each token index to a dense vector representation. Okay, so this is getting more complicated. For example, given an input sequence of word token indices like 245, we can first map these indices to their corresponding word embeddings, like blah, blah, blah. These embeddings can then be used as the V tensor in the multi-head attention layer, while the Q and K tensors can be derived from the same input sequence with additional projection matrices, which helps the model learn. Yeah. Okay, so can you walk through a smaller example step by step? Okay, that's quite a long. So okay, so let's take a small example to understand how multi-head attention works with QK and V. Suppose we have the following input sequence, and for simplicity, we'll assume that each token is represented as a scala value. Okay, but these are, in my case, okay, so, but I thought these were already the embeddings. You know what I mean? I thought the tokens were already the embeddings. So we have an input sequence, and we assume each token is a scala value. In our case, each token is a D model array, okay? 10 dimensions, yeah. So the first thing is like, and we have word embeddings. So this is what we don't have. And we have word embeddings. Okay, so maybe this is then the vocabulary. You know what I mean? We can use these embeddings as the V tensor in the multi-head attention layer. For Q and K tensors, we need to first project the input into higher dimensional spaces. Okay, so that's correct. Oh, so this is okay. So this is wrong. So what we're doing here is wrong, as in like here this is wrong. So this is okay, but this is not what we're doing. So this could be, so this needs to be like, this needs to be some sort of, yeah, whatever these embeddings, right? So we can use these embeddings as the V-tensor in the multi-head attention layer. For Q and K tensors, we need to first project the input into a high-dimensional space, 16 dimensions. Here, W, Q, and K are projection matrices of 16 by 1 and 1 by 16. Respectively, the product with the input vector produces two tensors of shape 116, which are broadcasted to match the same shape of the V tensor. 5, 116. The dot product between Q and K tensors measures the similarity between input tokens. Correct. We understand that. The resulting attention scores matrix, A of shape 501, is obtained as this, where the shape by Q tensor multiplication. The scores are then normalized in softmax activation function. We do this already. This is done somewhere in dot product attention here. The softmax. The attention output tensor. Finally, the attention output tensor is obtained by multiplying the weights matrix by the V tensor. Why? Why is the attention output tensor? Well, I mean, this is being done here, right? That's okay. That's like the dot product, whatever it is, right? So is obtained by multiplying the weights matrix by the V tensor. This step produces a weighted sum of embeddings, where each weight corresponds to the importance of the corresponding. Okay, so this is where I get lost. So each weight corresponds to the importance of the corresponding input in predicting the output token. But how? You're you have an attention matrix. Okay. So I need to clarify. The embeddings for each of these tokens. So what are the embeddings then? Can you elaborate a bit more on what the embeddings are and how are they calculated? Sure. In natural language processing, an embedding is a representation of a word or a sentence in a numerical vector space. The idea is to have words with similar meanings share similar vectors. So semantically, similar words will be close to each other in vector space. It's a representation of a word or a sentence in a numerical vector space. The idea is to have words with similar meanings share similar vectors. Okay, so but this means this is something that I need to have. I need to pre-calculate. So this is indeed the vocabulary. There are various algorithms available that can be used to calculate these embeddings, such as word2vec, GloV, and fasttext. These algorithms process large amounts of text data to learn the vector representations of words. During the training process, the model tries to predict the context or neighboring words of each word in the corpus, capturing the word's contextual meaning and producing the corresponding vector representation. Once the embeddings are calculated, they can be used in various natural language processing tasks, such as sentiment analysis. Okay. If So is it better to calculate the embeddings using your own training data, or is it better to use separate corpus of input text? So it is generally recommended to use pre-trained embeddings that are learned from a large corpus of text. Pre-trained embeddings are usually trained on a massive amount of text and capture a broad range of linguistic information, including syntactic, semantic, and pragmatic information. Because of these, pre-trained embeddings can be used to provide excellent performance on a wide range of natural, even if the amount of training data is small. However, in some cases, pre-trained embeddings may not be suitable for specific tasks with the native language. In such cases, use your own data to learn embeddings may be more appropriate. I got some more data set you can use. It has transfer learning techniques to fine-tune pre-trained embeddings. Okay, so fine-tuning allows you to tweak the pre-trained embeddings by training them. Okay, so okay, now I get it. So if I use pre-trained embeddings, but I mean, I thought that is what the tokenization. So in our code, in main pi, we have a tokenization section where we transform words into tokens. Is this the same as the embeddings mechanism? Because what we're doing is we're tokenizing it. So or is it that after positional encoding you're getting the embeddings? You know what I mean? I'm confused as in, like, is it what we're doing here, or tokenization is not an embedding mechanism? It's true. Tokenization is the process of breaking text into tokens or subwords, which are the smallest meaningful units that a model can process. In our code snippet, we're splitting the input sentences into words and then representing each one as elastic codes. What embeddings, on the other hand, are dense vector representations of words that capture the meaning in a high-dimensional space. Embeddings are typically trained on large corpora of text data using unsupervised learning techniques. Okay, in our code, after positional coding is applied, we have a tensor representing the input sequence with information about the word position. We then use this tensor as the v-tensor in the multi-head attention layer. We can train the word embeddings on a much larger data set and then use them to generate the v-tensor from multi-head attention by simply looking at. So essentially, this tensor as the v-tensor in the multi-head attention layer. In our code, after positional encoding is applied, we have a tensor representing the input sequence with additional information about word position. We then use this tensor as the v-tensor in the multi-head attention layer. We can train the word embeddings on a much larger data set and then use them to generate the v-tensor from multi-head attention by simply working out the corresponding embeddings for each word index. Okay, so what I'm understanding is, yeah, no, okay. So okay. So what I'm understanding is, I think what we have here, sort of after the positional encoding, is like you could use embeddings to improve these. It's okay. It's okay. It's like, so we could use we could use so we could use embeddings before positional encoding. Okay, so using embeddings before positional encoding would be an alternative strategy. Not using embeddings and just staying with simple ASCII representation is okay, even if that performs worse. Right? Yes, if embeddings before position equipment is a training strategy. In fact, using what embeddings as input to the multi-head is common practice. Capture yeah. Can be found across long as the system results. This specific task is going to code to make it be perfectly because it's easy to interpret and explain how the model works. Okay, yeah. Okay, at least we figured that out. Okay, so I would say input ID. So before here, so you know, here's like to use embeddings. Let's see how much it improves. It still doesn't solve my doubt about. Okay, so but we use so the v vector, right? Okay. Let us assume we just stay as we are and use the input vector, um, the input tensor directly as our v tensor. That's what what I don't understand is how to structure what I don't understand is how can attention weights be used to obtain a prediction. Like the attention weights are basically telling you sort of how tightly how much sort of a word predicts the other word, right? The attention weights tell you how much each word helps predict a given word. But if we multiply these attention weights by v being input tensor, how can we interpret the result? Like that's so the attention weights tell us how much each input word contributes to predicting each output. Okay, wait a second. So maybe what we have to do is we gotta actually have a split between input and output. Huh. Okay. Okay, maybe. But it's not really clear how to interpret the output of multiplying the attention weights by the input tensor. The output of the multi-head attention layer is computed as the weighted sum of value tensors in the attention weights, and this output can be interpreted as an interpretation of the input sequence that is optimized for a given downstream task. The intuition here is that by weighting the importance of inputs differently, the attention mechanism can better focus on the most relevant inputs for the current task. The output of the multi-head attention mechanism contains information from all inputs, but it's emphasizes those inputs that are most important for making predictions. To use the multi-head attention mechanism to make predictions, you typically feed the output tensor through one or more additional layers of neural networks. The final layer would typically produce a probability distribution over the possible output classes for a classification task of real valued output for regression tasks. So let's focus. Okay, so because essentially what is happening is Q. So we're giving basically the same value to these, right? So we're computing the dot product between the query and the key tensors. This is what I don't understand. So this masking is here. I'm just having, like, the thing is, I'm just having a basic algorithmic blank right now. So you know what I mean? So it's like if my, so let's focus on the distinction between input and output. Because in the architecture, it's like output embeddings, which are basically outputs shifted right. And then it's this masked multi-head attention. It's like it runs through two steps, right? The input embeddings and the output embeddings. Yeah. So these are the tokenizations, so to say, that the embeddings, yeah. Hmm. Hmm. So input and output, and how to map these two, Q and K then. Walk me through an example where our data set is a set of 4 sentences, like the ones and API, there are all the sentences. Okay, so let's start reading. So first sentence, and so let's walk through an example for the sentence: the quick brown fox jumps over the lazy dog, and the quick brown cat jumps over the lazy dog. To keep things simple, consider a single head attention mechanism, which means that we'll be computing the attention scores between query and query token and all key tokens. We're computing the attention scores between the query token and all key tokens using a single set of learnable query and key matrices. First, we need to decide on the choice of input and output for our task. For example, suppose that we would like to classify sentences based on whether they contain the word fox. We can represent our input as a sequence of word embeddings for each word in the sentence, and our output is a binary classification label indicating whether the sentence contains the word fox or not. No, okay, so that's not what we're doing. That's the problem. So, no. Okay, so rewrite with the example. but having in mind the goal is to do next word prediction. Because that's what I'm thinking is like this. A lot of these things are just basically what? Ah, okay. Okay. Uh-huh. No, that's not what I want. It's a word frame. Cool. Um, no. Uh, okay. So let me just ask. So let me just re-ask this tab. So that's not what I meant. That's not what I meant. What I mean is I'm having, that's not what I meant. For example, since we're doing that, but in how I or for example, my goal is to use the formats idea to implement next prediction. Maybe I should have started this off in the very beginning with this specific goal in mind. I think Ghostwriter got a bit lost there. As in like I think what we have in here is just for something else than that word prediction. You know what I mean? I wanna. I don't want code. I want a step-by-step tokens. It's funny with these indices. I was asking about these indices again. Interesting. So now it's actually, I mean, before I ask it, like it's actually asking me, it's actually suggesting that I have a unique index of the words through the kind of vocabulary. Split the input sequence into examples and targets. Create the precision encoding layer. Apply the precision encoding to the input tensor. Okay, so now we have an output tensor. Okay, so this is a slight modification. So create a multi-head attention layer, apply the multi-head attention to the input tensor, reshape the output tensor visible by the dense output layer, create the output layer of the network, and the vocab size. Okay. So we're getting something somewhat actually. Where's Y being used? Define a custom loss function, whatever loss function it is, and the train step. Containers. So, okay, this is the tokenize inputs into individual words and create a vocabulary from them. Okay, so this is what I was missing here, exactly. Convert each word in the input sequence. Convert each word in the input sequence to a one-hot vector and split the input and output sequences into training examples. Apply a positional encoding to the input tensor to give each word some context. Exactly. That's done. Pass the encoded input tensor through a multi-head self-attention layer. Reshape the output of the self-attention layer to be used by a dense layer with a. Okay, so that's kind of the magic, right? So reshape the output of the self-attention layer to be used by a dense layer with the size of the vocabulary. So are you telling me that the attention then Apply positional encoding to the input tensor. Apply positional encoding to the input tensor. Give each word some context. Yes. Pass the encoded input to a multi-head attention layer. Is it that then we're mapping with a neural network the attention stuff? Okay, guys, give me a second. Okay, now I'm just give me a second. This is paused or unpaused? I think it's now. No, I think it's recording. Okay, cool. So let me mute myself for a second so I can see the help. All good. Anyway, we're finishing. So it seems like it's reshaped. So the reshape the output of the self-attention. So what I was saying is like, is it possible that what we're then doing is we're mapping an attention tensor to an output? You know what I mean? Like I never thought about these like that. So is it that then we're doing multi-head attention, and this attention is actually fed forward, and uh, this doesn't actually. This architecture is a bit vague because it also doesn't really the output probabilities. The output probabilities, I guess, this is all with the vocabulary, right? So okay, so actually all you need is attention, as in like you're so you apply positional coding, you pass the encoded input tensor to a multi-head self-attention layer. That is actually crucial because I think this is really going to help me understand kind of the real gist of how that works for next word prediction. So pass the encoded input tensor through a multi-headed self-attention layer, reshape the output of the self-attention layer, the output of the self-attention layer. Because one thing that it does is, okay, so you actually have this attention thing. But it's true that like it's not so trivial to interpret what it means to apply. So you have this self-attention, you have this attention, sort of this attention tensor. You apply it to your V tensor, which is what? Which is the vocabulary? No, also not. You apply it, or you apply it to the V vector. I don't know what the V vector is now. Because what is happening here is create the output layer of the network. Vocab size. Reshape the output of the usable by the dense output layer. So you have the output. It's still XXX. It's still using the same thing. So you're applying your. Okay, so you just have to think about taking the attention, then multiplying these attention weights by the actual sentences themselves, right? So this essentially, okay, so essentially what this does is it encodes, it adds more information, right? So it's essentially telling you, it's all still input pre-processing. It's quite crazy actually. That's not what you're not training, but it can be, right? It can be because then what we're getting is shit here. It's like, This is what are you doing then? You're taking basically you're taking the output of the self-attention, which is, let's assume that it is the same sentences multiplied by the attention tensors. Um, and then you just have to actually train a neural network on top of that. Because you then have the outputs, because it's pretty good, your training examples are these, and you're saying, well, if my input looks like that, then the next word that needs to be predicted is like this one, right? Which the output of the self-attention layer is the dense layer with the size of the vocabulary. Calculate the loss using a custom cross-entropy loss function that incorporates mask padding and smoothing. This is going to take 10 years to implement. Train the model using an atom optimizer. Cool. Okay, so I think I understand now better. So this means, so essentially, the self-attention or the attention mechanism is still part of input preparation. And the learning and the learning really happens in a neural network between that transformed input and the potential networks. So the attention mechanism is used to help the neural network focus on the most. Okay, I think I understand that. The attention mechanism is used to help the neural network focus on the most relevant parts of the input sentence during training and to generate output activities during interface. The neural network learns to make predictions by processing terms of input sequences and sequence returnable layers. Okay, typically with one or more. Fine. Okay, now I get it. So the actual training happens it's just a neural network. So this is just input pre-processing. So all I've been doing now is just input pre-processing. But still, I don't understand how can you rely on this attention mechanism when you're just doing random projections, right? But how can you rely on the attention mechanism when it is based off of projections of random uh, higher dimensionality projections. Do you also train that separately? You know what I mean? Like multi-head attention, like this step here, right? So we are essentially randomizing stuff. Like we're essentially creating some random stuff, and then we're projecting the input into these random high. The multi-head attention is, for example, uses learn parameters. Learn. Okay, so uses learn parameter matrices. W you can to project the query. Yeah, but okay. So what do you learn these matrices, man? Bro. During training, these projection matrices are optimized by backpropagation, okay, to minimize the loss of the output. But this means, okay, so these are learned, so these are indeed learned. Uh, So train step, loss function, apply variance. But in the code above, we seem to only apply the gradients to the final layer of the how how do you to learn the optimal view? You know what I mean? However, buffer provision is used by the ultimate to compute the gradients or the loss with respect to the weights of the neural network, including why, as it updates the weights of the neural network during training, it indirectly updates. What the fuck? How? Since the forward pass of the multi-head what? Okay, that's for next session. So how is this supposed to? I don't know. That's not. That doesn't seem true. I don't. As the optimizer updates the weight of the neural network during training, it indirectly updates. That just makes no sense. Like you cannot indirectly. Like what do you mean? Like if I just do this multi-head attention and I'm just like, uh, you know what I mean? Like either I change these or I change the neural network weights. Like that's what I'm. That's. But okay, at least I've learned the following. So I've learned like what we're really doing here is yeah. So what we're really learning here. So what I'm learning here is that there's a lot of work to do still. Definitely, I've been just doing pre-processing all the time. I mean, let's just focus on some of these parts, okay? Let's just go ahead, not just dive into like, um, you know, over analyzing this stuff. There's definitely stuff that I need to do here. So we definitely need to do the assign an integer index to each unique word in the vocabulary. So we need to actually find a vocabulary first of all. So we need to create a vocabulary. Then we need to assign an integer index to each unique word in the vocabulary. Convert the tokens to one-hot vectors. Split the input sequences into examples and targets. So we need to actually start here, and then we would, and then we can erase these pieces. So that's kind of going to be the next. So let me just copy these and create a new file called next word thread example Python, and let's just use these in here, and yeah, so we have that open next time. So this is, we need to use these to basically adapt our name Python, and then just do that. Okay, okay, because it seems like, you know, with this name of fox, cat, you know, like for the hell it's dog, cat, it's rabbit, the fox, things like that. Yeah, yeah, I think that's a funny, that could be like a good small example. Just to understand this better. But it seems like the high level steps, what I need to do is basically, I need to figure out whether, like how to, so build an actual vocabulary, then split these into training examples, right? And I could do this like with this kind of, you know, windowing these things. And then essentially, I'd still need to build this kind of like dense layer. Or that is already maybe. whatever it is. Tension weights, output. That's already the output. Is it? No, that's not. I need to take the output and pass it to the translator. That's what I need to do, actually. And I need to kind of take this output and then learn how to adapt this output to improve or to predict the next word. Okay, not 100% sure, but at least one thing is clear. I've just been doing input pre-training, input pre-processing.